Hi, everybody. Welcome to our last day of the Battery Week. Today's talk will be focused mainly on trust of AI in the space of battery engineering, how we manage like explainability, transparency, and confidence. We will go a bit beyond just the battery. We will also explain other use cases that are aligned with engineering the domain. Today's talk will be structured the following way. So we first have a quick introduction of sphere energy in general and who is actually talking to me. So I'm not the only one giving the talk. I brought with me Svenja. Later to this a bit more. Then a broad topic, why we even need AI in the broad space of engineering, but also in the world of batteries, where we can basically transform traditional processes and accelerate them. Then we identify three key pillars of trust in AI. So the mathematical trust, the cultural trust, and also the regulatory trust. Then we conclude our talk with a bit going beyond the test bench, and then we are open for questions. So if you have during the talk any questions, feel free to write them into the chat so you don't forget them, and we will read them in the end in the Q&A session. So sphere energy is basically split in different offices. So we have, first of all, our test center in Augsburg. We heard in the beginning of the week on Tuesday a bit about our testing capabilities. We have the AI hub and data hub in Zurich and Munich together. So there we have our core competency in AI and data science, and we have a small engineering hub in France. Sphere Energy has many different domain expertise. One of them for sure is the smart data management. So all the data we collect in our test center, we have to manage. And then this data can be used for training artificial intelligence, so künstliche Intelligenz in the middle, right? And these AI models can then be used to inform the data generation, so to basically build smart test matrices with artificial intelligence in mind. We have a proven track record with a lot of collaborations with over 50 clients. We are certified with a common certification, and we are building currently an AI operating system that integrates all these things vertically. So who is talking to you? So I'm Dr. Oliver Schilter. I have a PhD in chemistry and AI. I'm here, the lead AI architect at Sphere. So my job is basically to develop the next generation of AI models with trust and in mind already. And I brought with me Svenja.
Oh, hi everybody. I'm Svenja Fischer. I'm at Sphere Quality and Process Development Manager. I'm mostly responsible for our certification all along Sphere, and I'm experienced in the whole value chain of battery production, of the whole battery production life cycle in the department quality management system. And yeah, to start our presentation, it's like, Ollie, I have a question for you. Why do you think we need a change in engineering? So why do we need AI? So the last 40, 50 years of development was working without AI. So
Right. This is an excellent question, right? We usually have following in the engineering domain, we follow the traditional V process. So this starts with requirements. So we get some documents, for example, then we build a design based on these requirements. We actually implement it. We test this design, and then the last part is validation and certification. And this is a very traditional approach to engineering problems. But we see that we have economical pressure, right, from other countries, let's say, or continents, that we need to stay competitive. So we need to accelerate all in the engineering process. And the tool that I think most commonly is used nowadays is AI. And we can use AI along this whole engineering process from, let's say, requirement engineering, using AI to extract information from PDFs to then also inform the design automatically, for example, to automatically design 3D parts to build them. And actually, where we also have a lot of expertise is in AI for testing, right? So it's the cell testing use case, build a model to test battery products. and then in the end also validation. But the key of this is, right, that we can use artificial intelligence reliably, is that the AI that we use for these processes needs to be trustworthy, right? Because if the AI gives us bad designs or wrong requirements, this doesn't accelerate us, but actually hinders us. So in today's talk, we want to talk about the three pillars of trust. I hinted them already in the introduction a bit. The first is the mathematical or statistical trust. So these are the classic metrics I think most of the machine learning people know by heart. Then we identified in a lot of our POCs and projects with clients that there's also a cultural trust, right? You cannot give somebody a tool and expect them to blindly trust this tool, but it's an iterative process. We identified that the people also need to have a cultural trust in this. And then last but not least, we have the regulatory trust. So there is more and more regulation coming towards us, that we have a fair AI system that treats, for example, in the case of, let's say, human data, everybody fairly and is not biased towards certain conditions. So, right, we always compare AI against the physical tests, but the physical tests themselves are also not flawless, right? Because we cannot test everything. So maybe Svenja, can you explain us a bit more why the limitations of what are the limitations of physical tests and why we cannot blindly trust them either?
Yeah, so as I mentioned, I'm responsible for the quality and process development. I'm mostly related to our test center. And as I started to visit the topic AI and trustworthiness, I was like, yeah, so why I should trust AI and not physical tests. And so I found a lot of good reasons why physical tests are like not so trustworthy as we are thinking about. So for this, I have kind of three good reasons. So the first reason is like the combinatorial explanation. So it is, I have at the battery itself has a lot of different variables about the charge rate, the chemistry, the temperature. So, and these are like a lot of variables inside the battery, but we know the battery is not in the perfect room. It's mostly used in cars, power tools, wherever. So we have like a lot of external variables like the temperature, the pressure, like how we treat the battery, are we doing fast charging, slow charging? And we are seeing it is like getting a lot of different variations. So for example, if you want to do a test at different temperatures. We can test like 15 degrees, we can test 30 degrees, we test minus 10 degrees for the kind of one option of fast charging. And then we're having like exactly three tests, but we only have like three temperatures. And it's like, okay, but we have so many different options on temperature. So it would take like a lot of different tests. And there we are coming to the second reason why we are like limited on physical tests. We have like a physical ceiling. So if we want to test 1 hour testing the battery is like 1 hour of our real time. So we only can test 24 hours per day because the day has only 24 hours. So there's no possible acceleration of the testing. So it's a linear movement. And the same is if we say, okay, we have the same time, but maybe we can do more tests. Yeah, for sure. You can buy a lot of more test channels, for example, at battery and test like million of cells. But we will see our costs are getting exploded. So it's nobody will ever prove if you say, okay, I would like to test 1 million different scenarios. And with this, we are coming to kind of a silent risk because now we have to decide because we have this physical ceiling and we have this a lot of combination. We have to decide which test we would like to do. And so we are sticking normally to things we are knowing, to standards. So for example, with the temperature, in Germany, we are used to, I don't know, maybe -5 degrees to 30 degrees in summer. So it's like a real usual range, but we are going to Finland. So we are having like -10 degrees, like not like in Germany, maybe 2 months. We have maybe if we go to northern Finland, like 6 months a year. And then we are like, okay, now we should test the battery, like if they are getting more cold starts or like also more charging in really cold environment. But you can't test it because, except as I explained before, I have two good reasons why I couldn't test every use case. So I'm sticking to my standard tests, and I'm only validating things I'm expecting, and I'm not validating things I'm not expecting. So all in all, we are, yeah, if we continue with only trusting physical tests, we're having the problem that we will lose a lot of money and a lot of time. So we are too slow to in our development to develop the new generation of cells, for example. And yeah, that was, I think that were really good examples why we should change our mind and not saying, okay, I'm only trusting physical tests, more to think about, okay, what are good reasons to trust simulation and the AI systems and not only the physical ones. So, and I think, Ollie, could you explain maybe the first kind of trust that we can now move forward to test AI systems?
Thank you very much. So, as Svenja explained in detail before, right, we have this problem that our, let's say, design of experiment matrix for battery validation has holes in them, right? Because we cannot test all the different combinations. So this was a combinatorial explosion. And exactly there we see the potential of our AI systems to actually fill the holes in the test matrix and test the unexpected, right? We can, because these tests don't cost real money in terms of comparatively to battery tests, right? They are just using a model. So we can test way more and way broader. And also we are not bound to the physical ceiling, right? If we want to simulate with an AI model the aging of a cell for, let's say, 1,000 cycles, this takes a couple of minutes and not 3, 4 months. So this is exactly what enables us from our battery model. If you want to learn more about the actual underlying architecture, we had yesterday a talk from Gianmarco that we will share later the recording with you guys if you want. So if you sign up, we can send you the video of all the talks that go more in detail what is underlying in the AI model. But I just want to here highlight, we can actually fill the gaps of the test matrix with AI models. But for this, our AI model needs to be mathematically certain, right? We need to know that our model performs as expected. And we usually use in the space of AI traditional metrics. These are on the left side, right? This is basically we take some samples that were not shown to the AI model, so our model didn't see them during training, and we use this holdout test set to validate our model. So these we measure, right? And then we look how good our model predicts compared to the real world scenario. And we do this with certain standardized metrics like mean absolute error, where we compare how far the curves are off in terms of here in ampere hours. But this can also be normalized to percentage, then it's the mean absolute percentage error, or we can use the coefficient of determination to see how well the two lines correlate. But we here at Sphere, we actually do also uncertainty estimation. So in uncertainty estimation, you don't only get the raw prediction of the model, but you get actually a confidence interval. So we know how certain our model is in each cycle, in its prediction. And usually the confidence interval obviously grows the further along we go in the battery cycling campaign. So the more we cycle, the more uncertain the model gets, which makes sense. And with this, we can kind of estimate how good our prediction is. But we go even one step further, right? Because we don't want only uncertainty, but we want also explainability. And we know from talking to battery engineers that usually they trust the physical models a bit more because they can understand what happens. So our AI model actually predicts then a physical model that is the same as the curve it predicts. And with this physical model, so these are P2D models with degradation mechanism, we can actually understand what is going on inside the battery. So we gain the explainability of our AI systems by understanding, okay, what is actually causing the degradation loss? Is it like ACI growth? Is it loss of lithium? Is it like lithium plating and so on? So this helps to actually reason about our AI model's prediction. Right. And this comes to the next point, right? If we have such a model that we can use for these predictions, we know from other client experience that we cannot just go to a battery engineer and say, don't test any batteries anymore. Let's just use the AI model. The trust in this model needs to be gained from a human perspective. Even if the metrics looks amazing, we need to experience the metrics to believe it, right? And this is what we experienced and what we usually suggest clients to do, to run the first iteration of battery testing with the simulation model simultaneously. So you don't save any tests, but you run the test and compare our model's prediction against these tests. And we can even use these tests to refine our model. But the main part is that then the battery engineer sees how good our model is and gains trust in a model. And then in the next design of experiment matrix, he's maybe confident in the model. Maybe let's do only 70% of the usual tests. So instead of 100 different test conditions, we only test 70, and the remaining 30 we only simulate. This is an iterative process, and we are not the first industry that experienced this. The classic example usually is car crash testing. So 20, 40 years ago, we only tested car crash by basically smashing new car models against the wall and see the effect on the physical model, right, on the car. But then computational simulation came in and basically iteratively replaced some of these very expensive car crashes with simulations, right? And the battery and the crash engineer probably experienced, okay, he can trust more and more the simulation because the real world and the simulation overlap. And the same will happen in the space of battery. So with this, we want to highlight again, right? The more the engineers experience the accuracy of an AI model, the more they will trust its prediction. And also this leads to this cultural change and cultural trust in these AI models. So besides mathematical trust and cultural trust, we also have a regulatory aspect. Maybe Svenja, can you tell us a bit more about the new laws and regulation that the EU has in mind for AI systems?
Yeah, thanks. Exactly. So as already mentioned, the European Union published in August 24 a new law. It's the first AI law. It's called European AI Act, and yeah, that's really interesting because it's the first AI law like worldwide, not what the EU published. And it can help us a bit, or it should help us all also to gain trust. So they want to give us a framework how AI systems should work. But I think it's a really good framework how we can still build trust in AI systems. So, and it's helping us exactly to turning a black box in a transparent engineering tool. And I'm talking now about one chapter of the AI European AI Act because it has around about 400 pages. And I decided today to talk only about the AI high risk systems because battery testing is safety critical testing, also crash testing. We all can imagine how safety critical it is. So we are coming to these 5 pillars, which are in the chapter 3 exactly. And it's about the data governance, the transparency, the traceability, the technical robustness, and the human oversight. And it's really interesting because all are like kind of linked to each other. So if we are going to the first pillar of this 5, we are talking about the data governance. So the European EU AI Act want to set some standards for the trainings data. So it's a bit along like garbage in, garbage out. So it sets standards that the trainings data need to be representative, that need to have like a really good quality. It needs to be checked. So you can't download the first set you would like to have from the internet. You should definitely check if it fits really to your use case. And with this one, transparency is linked because now it's really important that you can explain how the AI started their decision. So, and you can show the persons, and that's linked to the cultural trust, how the AI is acting and how they are coming to their results. So it's really good for human understanding. And also you can see if you make a transparency which data sets you use, the human also has like kind of trust again, because if he sees the data set is like really clear and logical and a really good data set, he can see, okay, it's really good, so I can trust it because it's useful data which they're used for training. And with this together, we are kind of traceability, because if it's a set, if everything is traceable, so the human can open kind of a book and say, okay, I saw you documented you used the data set A, B, and C, and I know this, and I also see how the AI made their decision. And the important point, I also can see if I thinking 2 years about my test from, for example, today, I can see, okay, it's nice. I can open the log. I see every decision, and I can still trace my the decisions. And I also have the record of changes, so I know tomorrow I'm opening my AI and it's deciding differently. I can see, okay, there was a software update. I can see directly what changed, and I also can see how it's influencing now the decision making. So I having like again this kind of trust. And with the fourth point, I'm coming back to the trust Ollie explained about mathematical trust. So I'm having the accuracy, so that that the system will be working like I can see how it's accurate, and I can see is it technically robust. So it sets a framework. It has to be technically robust and has to work on physical laws. So as Lawrence and Kais on Wednesday we presented our P2B model, you can see we already set the standard that our model is working like in a physical normal way and is not doing some hallucinating, like for example, we know ChatGPT 2 years ago was giving some crazy answers about some questions, and today we know that our model will never simulate, for example, that the battery will have the best working condition at 100 degrees Celsius. So that's like kind of giving a framework. And I think the last one is like giving is summarizing all four pillars. It's about the human oversight. So you're taking the human in the loop. So you never say, okay, I want to do everything without the human. It's getting, it's more about to make the human more efficient. So he needs not to check all data points by himself. So he can start and check only the anomalies the AI system pointed him out. And so he has to focus on the really important point and not to work on really normal use cases where the decision is kind of clear. So yeah, and I think this is a really good framework we can use, that we having like that we are having like our three pillars, like the technical, cultural, and legal pillars work all together to trust more in AI. And yeah, with this, we would come to our summary, I think. So, Ollie, what do you think is the best summary today?
So again, right, we want to highlight in the first part of the talk that maybe physical tests are like excellent, but we cannot do them exhaustively. They come with a high cost, and they are bound to the physical laws in the sense that if you need testing battery, it takes maybe half a year, and we can maybe not afford this time. So with this, we highlighted that AI can actually help us fill these holes in the test matrix, maybe even reduce the test matrix and gain insights faster. So, right, an AI prediction again takes minutes, not hours and days. We can only do this if we have the trust mathematically and from a statistical point of view that our predictions are accurately. Right. If we have then this accurate prediction, we need to foster a cultural change that also engineers trusted predictions of AI, and do this iteratively, where we replace part of the test matrix and showcase that actually the model is capable of doing this and foster this cultural change. And last but not least, very important is again this, let's say, regulatory trust. So to have traceability, accountability, and so on in your whole AI pipeline to be sure that all the processes are followed from, let's say, a regulatory standpoint.
Okay, thanks for your conclusions. So we are coming to our Q&A time, and the first question is actually coming from me. So it's about the mathematical trust. So we have this accuracy level where we say we can trust the AI, but how it is set. So can we set, okay, it's good if it has an accuracy of 95%, or is it better if it has a 99.99%? So is there some framework which like set standards or something like this?
That's a very excellent question, right? The level of accuracy or let's say predictability of our models, how precise they need to be, differs very depending on the use case. Just for example, if you're in a full like cycling campaign that of a battery that should be going into a car in the next couple months, years, then we need a different level of precision on a model than somebody that does it exploratively, let's say screening batteries to be just sure it lasts at least 500 cycles for, let's say, a power tool. So they have different levels of traceabilities. What we aim on the highest level, right, on this life cycle cycling, we try to aim to be in the same order of magnitude than the physical test noise is, right? So what I mean with this, if we test the same battery twice at the same test condition, it can be that there's slight variation in, let's say, manufacturing tolerances, maybe in raw material of the battery. So we have a slight deviation, even if we test the same battery at the same condition twice, we can have a small, let's say, deviation between the different replicas. And our models, our goal at Sphere is to aim in the same level of precision as this physical test from an order of magnitude point of view. So we try to be as accurate as physical tests. We are usually very close to this.
Okay, thanks, Ollie. And I think that is kind of a open discussion because the EU AI Act is kind of open. Like you have to define the standards by yourself. So like where the accuracy is set, but I think there's maybe missing kind of way of working how to set this definition. But yeah, so all in all, thank you everybody for your attendance. And we are now ready for questions.
So I see there are already a couple of questions. So if you have any more, feel free to type them now in the chat and we go through them. So I will pick the first one that was about, I think there are two in a similar directions. And it's about how we can be certain or how we deal with the factor of trust if we test new cell chemistry. So completely, let's say sodium, iron, and stuff like this, right? We have to be transparent in a way that if we know already, right, the chemistry is not in our base model, we can be also very certain that this is not trustworthy prediction, right? But we can actually do this also from, let's say, a more AI engineering point of view. We can do this in a concept called guardrailing, where we look at how different the input is to what usually the model experienced before during training or fine-tuning. And we see if we go very far away from this scope. So again, in not just a different NMC cell, but like a completely different chemistry. We see in this point already that our model is most likely not trained on it. And then we can already inform the user with like a score between 0 and 1 that the cell is most likely not very trustworthy, the prediction, since the chemistry was not yet in there. Interestingly, I just want to open this discussion quickly. Interesting, right? We can also use our knowledge about testing and AI to actually inform a smart test matrix. So we know, for example, that our model captured temperature trends and C rate trends very exceptionally well in a normal range, let's say from -10 to 40 degrees. So we can only test like anchor points. So we can already reduce the number of tests if we know we want to include a new chemistry, by smartly think about which extreme condition maybe needs to be still physical validated, but the, let's say, called interpolation between test condition, we know and are certain that our model is capable of doing. So we can already reduce the number of tests. Thanks for this excellent question. And I think, sorry, Svenja, if I take another one, we go into the next question, which is how many physical tests we still need to do, right? And we did this experiment with a couple of clients, and I think Gianmarco showed yesterday already the results in detail of these studies, which highlighted that we can ultimately reduce around 40% of the test matrix and still be in the range of the replica errors if we smartly select them. So if we reduce, for example, again, the exhaustive temperature screening and we do maybe only -10, 25, 45 instead of 0, 5, 10, 15, and I don't know, 35, 30. If we know this, right, we can reduce even more. But this is a bit, yeah, it's a bit biased, changing, but around 40% is a realistic number that we confidently experience many times, also for different cell chemistry, that we know that we can reduce the number of tests. So there is a question for you, Svenja. Sorry, I had to scroll a bit. So to take one that is maybe a bit more towards you. It's a question about do we already have ISO 42001 implemented at Sphere?
Okay, that's a really good question. So this is a standard which kind of belong to the European AI Act. And this is, yeah, it's really strong connected. I know there's coming an update that it's better getting more kind of harmonized, but yeah, so at Sphere we are currently working on it. It's that we want to implement it because we think that is setting a really good trust point at our AI models. And yeah, hopefully, yeah. So we are now really working on it with our partner together to have a really good implementation.
Thank you very much.
I think the rest of the questions are more related for you.
Like the one question is how can we close the gap between AI that is trained on tests and real world application like vehicles? How does trust in AI can be useful there, right? This is, I think, a very interesting question because we face this also many times in the sense that how is, let's say, the gap between very symmetric cycling in cycles towards the actual use case in real world cars. And what we experience here is that actually, obviously, battery cells are also tested with standardized driving protocols like VLTP and so on at different conditions. And some other OEMs have their proprietary driving profiles that mimic the behavior of cars that they recorded from a usage pattern, right? And our model is capable not only of symmetric cycling, but we can actually also use drive profiles to simulate the behavior of drive profiles. And we see also there we can use mathematical methods like uncertainty intervals and things like this to getting close towards like a certainty estimation also for these drive profiles. There is also work that is not yet fully fledged, but we are working also on, like, say, ECM models for the corresponding aging curves to also have corresponding, let's say, models that then actually can be used on a vehicle's battery system. Okay, so maybe we have time for like one more question. So there were questions about how we use our AI model and trust factors in application such as battery energy storage system. So again, also here it's similar to the question before, right? In battery energy storage system, we usually have the more challenges with like charging and discharging during the day and not like let's say symmetric cycling like classic cyclers. And we can also use our AI models for these profiles. This is not fundamentally different than drive cycling. Also here, the trust factor, I think, is twofold. First of all, we have, again, the output of our physical models. So we can get a physical models from our prediction. So these can also be done on, let's say, again, let's call them mission profiles as a broad term, so either drive cycling or best profiles. And actually, we can then use these physical models as well, for example, to gain insights into the cell, as well as mentioned before, we can use uncertainty estimation to get a certainty for knowing what is going on and how certain our model is in its prediction. So I think with this, I think Lisa mentioned, so our organizer mentioned that we should highlight again that we will share all the talks from the whole week as recordings if you want. They are freely accessible. So if you missed maybe the talk yesterday from Gianmarco about our AI models architecture, or on Wednesday about our new P2D model suite to automatically parameterize physical models, or our testing capability, feel free to listen to the recording. Thanks again for all the excellent questions. And I want to give the last word to Svenja also to close the call.
I want to say thank you that you joined our really interesting topic, and hopefully that you have now a new a way of thinking about testing, and not a bit think about beyond the test bench. Yeah, thanks everybody.
Thank you very much.